Sorry for the aggressive intro on the last video, you guys. We're trying a little bit better with a smooth, calm, relaxing introduction. Ba-da-da-da-da-da. Yeah, that is recording. It's all in there. Alrighty, so first, talking about limiting and excess reactants from more of a conceptual standpoint, let me pull up just a blank page to sort of write this out for you. If I had, let's say, a box of, oh, it's the right color too, graham crackers. I've looked into this and we cannot get a clear answer. I didn't actually go home and open graham crackers, but I cannot figure out for the life of me how many sleeves are in a standard box of graham crackers. You know what I'm talking, like the tan plastic wrapped. I think that there are 3. That is what my gut says.
Search it up.
I know I did search it up and I found a bunch of different answers.
Wait, so what is it?
So what I'm trying to figure out is, okay, so if you're a graham cracker, like your single graham cracker, it normally looks like this, and you can split in half, and then there's like the dotted thing like that.
Yeah.
And then there are 8 of these, right? And then the 8 of those are like plastic wrapped in a little tan thing. And then there are a certain number of these inside your box of graham crackers. But how many of these are there is my question. Okay, let's just go with 2 because that's what my students said too. I don't think it's 2. I think that there are 3. All right, maybe I just get a big box of graham crackers. But anyway, so we'll say that there are 2. So if I have 2, we'll say sleeves of them. Oops, 2 sleeves per box.
Right? You'll find 26 large crackers, and if there's 8, it has to be by 3. So it might be
8 times.
Because it says you'll find in a 14-ounce box, you'll find 26 large crackers.
But that doesn't make any sense with this. 8 and 26 don't go together.
Yeah, obviously, but I mean, if it's 8.
All right, let's just see. We'll roll with it. We'll say there's 2 and that there's 8 because that makes it make sense. Okay, let's pretend that you are a normal person making basic, normal s'mores. Nothing crazy happening. With 1 sheet like this. The way that I drew it. How many s'mores can you make from 1 sheet?
8.
What? Like 1 sheet being this. 1 s'more, okay, because what you do is you snap it in half and then each s'more ends up with like this plus this, right? You could, but why would you? That's what I mean by being a normal person. Okay. Are you with me so far? You understand what I'm talking about? Like you can picture that this is the thing. Okay. That is my graham crackers. Based on this information, if I have 8 of these per sleeve and I have 2 sleeves per box and I need 1 total sheet to make 1 s'more, so 1 sheet equals 1 s'more, then how many total s'mores could I make from this box of graham crackers? Okay, so 1 box will yield 16 graham crackers. Oh, sorry, 16 s'mores. Basically. Are you following so far? If I'm going to continue my s'mores making, what other ingredients do I need? All right, we'll do marshmallows in what color? Red?
Oh, I was going to say white.
Okay, my marshmallows will be in this bag. I also searched this up yesterday and found that there are like between 60 and 70 marshmallows per bag. What it feels like is there are about 10 billion marshmallows per bag. And I'm talking about the basic Jet Puff marshmallows, like not jumbo, not mini, just the normal, regular, normal s'mores size marshmallows. You know what I'm talking about? Do you agree though that like there's like too many in there? Like
no, they're not too many.
There's so many.
There's so many. Yeah.
There's got to be more than 60.
They're getting their money's worth.
Okay, sure. Normal size. Okay, so these are marshmallows.
I don't know why you
Marshmallow.
Marshmallow.
That's the new brand?
I always forget how to spell it.
It's with a double
Marshmallow.
It's with a double
Wait,
E.
is it with an E?
No. It's marshmallow.
That's what I said.
L.
Anyway,
There's a W.
we've got all these marshmallows.
It's a W.
Marshmallow.
That's for you. All right. How many marshmallows do you want? Let's just agree on a number. How many marshmallows are in here? 60? Okay. There are 60 marshmallows per bag. According to only the marshmallows, how many s'mores should I be able to make?
60.
60. Okay, so according to this, I'll say 1 marshmallow per s'more.
Normal.
And so 1 bag, to be honest, I put 2 on mine, but that's beside the point. 1 bag will give me 60 s'mores. And then what else we have that goes with this that you cannot make your s'mores without is chocolate.
No, you can't. Why would you? You probably shouldn't. S'mores, isn't it like?
So Hershey's look like this. Like
You
that.
just had one yesterday. I didn't know they were. Oh, you still have it?
Yes. My students tried to argue me and say that there's not 3 rows of chocolate, and there are 3 rows of chocolate, and they split like this. Okay, so
Oh, wait, yeah, it is.
if you are my crazy husband, you use actually this much chocolate per s'more. So we argue about this, and he has to buy double the chocolate so that I have my own pack and he has his own pack because I am stingy with my chocolate and I only use this much per s'more.
Yeah, you use like a lot.
Yeah.
This is what a normal person uses.
For each s'more.
Yes, for 1 s'more, I use this amount.
How small?
Lena, what do you use?
I don't know, like 2.
2 squares?
Like hanging out.
Like this?
Yeah.
What kind of psycho breaks their bar like that? Like how? Like what are the logistics?
You
No.
don't break it like that. You see how there's like, there's like 4 like rows or columns,
Mhm.
like thing. So you break it by like 2 down instead of 2 to the side. It's 2 down for each thing. Like
You can still break it either way.
and then you break it into 3 parts. That happens in 3 parts.
That is absolute chaos. I will not be inviting you to my s'mores party. Actually, I would because then I could just have your leftover chocolate and we'd be
That's so
fine.
little chocolate, don't you?
That's what I mean. I think the perfect ratio is this much.
I think the perfect ratio is what you're. I
No.
think the perfect ratio.
This actually like fits beautifully under 1 marshmallow and on 1 sheet of the s'more like that.
Okay, well, how big are the graham crackers? 'Cause
Like a normal size graham cracker. I don't know. I thought that these were standard sizes. But then I started teaching this yesterday, and my students had such strong opinions on how many things were in each thing, and how you break your chocolate, and what you put where. And I was like, holy
this
cow.
is a graham cracker. This is the size of a.
Yeah, but then you break that in half.
Exactly. That's why you need like half of the bar.
No, so that's what my husband does.
Do you need anything else?
I do not.
How big
Thank
a graham
you.
cracker is. That's why you need half of the bar. You need the chocolate to out.
No, that is too much. All right. Anyway, so we're gonna make my recipe of s'mores, and if you don't like it, that's fine. You can go make your own s'mores at home. I use this much, which means that for every 1 bar of chocolate, I can make how many s'mores? Yeah.
Yeah, 4.
And usually when we buy these, like we are definitely suckers for like the grocery store marketing thing where they put your graham crackers and your marshmallows and your s'mores together, and they always have the 6-pack of chocolate bars. So it'll be 6 of those Hershey bars in a little pack. You know what I'm talking about? Okay. So that's typically what they sell with this, and so there will be 6 bars per pack. So based on my 6-pack of bars, how many s'mores could I make?
24.
Oops, 1 pack equals 24 s'mores. Okay, so now let's look at this big picture. One of these things, if I start making s'mores and I'm like, I'm going to have a s'mores party and I'm going to invite all of my friends over, how many friends can I invite over to have s'mores? Or really, how many s'mores can we make based on this stuff? I can only make a maximum of 16 s'mores.
But do you have 16 friends?
No, I don't. Thank you. Thank you for pointing that out. Do you have 16 friends?
No.
Well, welcome to the club. But that's okay because I can eat enough s'mores for 16
Exactly.
people.
And you can double.
Yeah, exactly. Double
Maybe
up.
even triple.
Maybe even triple. This is the quality of life I'm talking about. Yes.
Even quadruple if you only have 4 friends. Think about it.
What makes you think I have 4? You know, I was thinking all 16. Okay. I love this. You can only make 16 s'mores, but if I go and buy another pack of chocolate, is that going to help me make more s'mores?
Yes.
No.
If I go and buy another pack of marshmallows, is that going to help me make more s'mores? No, because what runs out? The graham crackers. So we would call this my limiting reactant.
But you wouldn't have enough chocolate. If you bought two boxes of graham crackers, you don't have enough chocolate.
So this is why we have to scientifically figure out the perfect ratio of s'mores things to buy based on the recipe for s'mores that you like. So limiting reactant is this one because it runs out. So I'm going to jump back to the notes. And like now that we have a little bit of context for this, the limiting reactant is the reactant. The reactant.
We could have done this with actual food.
That's what your project is.
Oh, wait.
So do you expect like an explanation like that? Like,
No, just math. You're just going to mathematically calculate it. We'll talk about the project at the end. All right, so the reactant that runs out during the reaction is your limiting reactant. It is called limiting because it will limit the amount of product that you are able to make. Sorry, that says it. Yeah, it limits the amount of product that you're able to make. Everything else is considered what we call excess reagent, or this really means the same thing as an excess reactant. The difference in words is just reagent is just like what we call our supply, and then reactant means it's like kind of involved or it's present at the reaction. So excess reagent is all of your leftovers. There will be some of this left at the end of the reaction. So if we apply this to my s'mores example, if I buy 1 box of graham crackers and 1 bag of marshmallows and 1 pack of my chocolate bars, and then I make as many s'mores as I can possibly make, and I just keep on making s'mores until I run out of something and can no longer make that recipe, then at the end, I have 16 total s'mores made, and I have marshmallows unused, and I have chocolate unused, right? The chocolate and the marshmallows that are unused, we would consider those excess reagent or excess reactant. We have more than what we needed. All right, so looking at letter C, this gives you steps to determine the limiting and excess reactants. So I'm going to refer to this equation right here, that A plus B yields AB, just so that we're making the same product. But looking ahead, keep in mind that you can have multiple products, or you could even have more than 2 reactants going into your equation. So your first step is that you are going to turn, I'm going to change colors, not for any real reason, just changing them to switch it up. So we're going to turn reactant A, and say turn the given amount. Given amount of reactant A into any product. I'll put in parentheses up here, look ahead, and we'll talk about what I mean by that. So you're going to turn the given amount of reactant A into any product. And you should look ahead to determine what product might help you. But really, it does not matter which one you choose. Then you're going to turn reactant B. I'm going to use a different color for this one. Turn the given amount of reactant B into the same product. Both of these are going to be moles. So when I say turn it into any product or turn it into the same product, you can stop when you're in moles. You can go in grams. It doesn't really make a difference, but we're going to say in moles for each of those. Then we're going to say compare your answers in the limiting reactant makes the least amount of product. The reason you can choose any product is because the limiting reactant would make the least amount of any product. It will be the same one no matter what. And then the key for this is that you are going to then, I'll put a star next to it, use the given information about limiting to calculate everything else. So I always go back to using the given. Here it technically doesn't matter if you use your calculated answer, but there is more chance of error happening there. So if you made an error in your initial calculation and then you use that calculated answer to do everything else, then it messes up everything else down the chain. But if you figure out which is your limiting and then you use the given information from your limiting, there's a chance that you can get yourself back on track with your calculations. So that's why I say go back and use your given information. So this might not make a lot of sense when we read it in words, but when we practice, it should start to make a little bit more sense. So if I go to, I'm going to pull green for my first color so that it matches step number 1. Actually, first, let's balance our equation in just a basic color. So we're going to balance SiO2 plus HF will yield SiF4 plus H2O. I'll wait for y'all to balance it. And then once you've got this one balanced, if you wanted to work ahead and balance the other ones, that works too. Has anyone finished balancing this one? What you got?
1, 4, 1, 2.
Do we agree?
Yes.
I do. Okay, so 1, 4, 1, 2 as our coefficients. Just like with any of our stoichiometry problems, you have to start with a balanced chemical equation first. So then in this question, it says if 2.0 moles of HF are exposed to 4.5 moles of SiO2, which is the limiting reactant? So what this is really asking is which one of these is going to run out first? And just like with our s'mores example, I like to talk about it in terms that you guys are really familiar with, because it doesn't mean that you're necessarily using the same amount of everything. I use 1 marshmallow, but I use 2 different squares of this, or I use 3 little squares of this. And so there are different quantities that we're measuring these in, so it just depends on what your recipe is. And in chemistry, your recipe is talking about your chemical reaction. So going to the color of number 1, so talking about this, it says turn the given amount of reactant A into any product. So we need to choose which product we want to make here. It does not matter in this question, since there are no follow-up questions, it doesn't matter which product we choose. So would you rather make SiF4 or make H2O? Okay, so we're going to take SiO2, and I'm going to turn that into SiF4. Separate from that, I'm going to use blue so that it's being consistent, I'm going to turn HF, my reactant B, into the same product. So our setup for this is going to be using the given amount of each of these things, turn them each into the same product so that we can compare our answers. So I'm going to take my green one, and I have 4.5. I think I'm gonna scoot over so I have a lot of space because I don't want to run out of room. So 4.5. If my pen will help me. Moles of SiO2. Just like in all of our other stoichiometry problems, I'm going to bring down moles of SiO2. And then I want to turn it into that product of SiF4, so I can stop at moles. That's why I put this part here, said in moles, so that once you get it in moles, you don't have to keep going. Because if you have less grams of something, you're going to have less moles of it. Or if you have less moles of something, you know you're going to have less grams of that same thing. So taking it to grams is just an extra unnecessary step in this case, unless it specifically asks for it. So then I would take moles of SiF4, and then I use my mole ratio. So for every 1 mole of SiF4, how many moles of SiO2 did I have? 1. So this just came from my balanced chemical equation. So then I don't even have to do any math in this one since they all cancel out. The 1s don't change my answer. So for every 4.5 moles of SiO2, I can make how many moles of SiF4? Perfect. I'm going to put words on this just so we have context. So 4.5 moles of SiF4 can be produced from 4.5 moles of SiO2. This way, when you guys are doing your homework, if you get confused about what these numbers are actually telling you, the words sort of tie that together. Then, in my other color, I'm going to take my other given information, my 2.0 moles of HF, and I'm going to turn that into moles of my same product. So I'm going to bring moles of HF to the bottom and put moles of SiF4 at the top. For every 1 mole of SiF4, how many moles of HF did we have to use? 4. So 2 divided by 4 tells me what? Good, 0.5. Or I guess 0.50 if we do sig figs. I didn't even look at that on this one, but it's the same. 0.50 moles of SiF4 can be produced from 2.0 moles of HF. So backing up, we did step 1 where we turned the given amount of reactant A into the product. Then we did step 2 where we turned the given amount of reactant B into the product. Then we need to compare our answers. The limiting reactant is going to be the one that makes the least product. So in this case, who would that be? It would be, which one? HF. Okay, so the least amount of product that I made was 0.50 versus 4.5. So this one definitely made less product. So that means that my limiting reactant is HF. It's the thing that I started with. So HF is limiting. Specifically 2.0 moles. 2.0 moles of that is my limiting. Does that matter? So if I doubled the amount, so sometimes if they're close, the amount matters, yes. So like basically what happened, if we compare it to this, if I were to buy more of this, then this would no longer be my limiting reactant. So your amount matters, yes. So I said HF is limiting, but I left that off, but this, in the context of the question, like that answers it, yes. So the amount does matter. Good? In this case, it doesn't ask us to calculate anything else regarding that question, so we can just move on to the next one. So there's nothing to do for step number 4. So then I have a new equation. Has anyone already balanced this one? What you got, Kate?
1, 2, 1, 4.
Do we agree? Perfect. All right, so example A says, which is the limiting reactant in this equation if 0.75 moles of N2H4 is mixed with 0.500 moles of H2O2? So I'm going to start with my green, the first one, and I'm going to turn N2H4 into which product? It doesn't matter. You want to do nitrogen? Okay, so we're going to turn this into nitrogen, and then what matters is that you choose the same product for your second one. We're going to turn that also into the same product. So in my green one, I'm going to start, over this way. So 0.75 moles of N2H4. I'm going to bring moles of N2H4 to the bottom, and I'll put moles of just N2 at the top. For every 1 mole of N2H4, I have 1 mole of N2. So my moles of N2H4 cancel, and I'm just left with 0.75 moles of N2 able to be produced from 0.75 moles N2H4. So the math itself is pretty straightforward. It is just calculating how much of your product you could make. So then I would take this 0.500 moles of H2O2, bring moles of H2O2 down to the bottom, and according to my coefficients, for every 2 moles of H2O2, I could make 1 mole of N2. My moles of H2O2 would cancel, so then I have 0.5 divided by 2. So 0.25 moles of N2 able to be produced from 0.500. I would need to add another 0 for sig fig, so 0.250. From that many moles of H2O2. So again, taking a step back and comparing my answers to one another. The least amount of N2 that I would be able to produce is 0.25 moles. Do you see where I got that from? Okay, so then with that, we can conclude that which one of these is my limiting reactant. So H2O2 is my limiting reactant, and so this is where I use the given information about my limiting to calculate everything else, since there are follow-up questions on this one. So question B says, how much excess reactant in moles remains unchanged? You have to actually think about the context of your equation when you are figuring this out. So excess reactant means, what is it asking about? Which reactant? Okay, so keeping that in mind, I'm going to say it is asking me for, so my final answer should say something moles of N2H4. When it says remains unchanged, that means that this is what was not used in the reaction. So if we go back to our s'mores example, I would get that by taking, okay, if I had 60 marshmallows and I needed to use 16 of them to make s'mores, then to find how much I didn't use, I would take 60 minus 16. Right? Same thing, I can do that with my chocolates as well. So here, I'm going to calculate how much I did use and then subtract it from how much I started with. So I'm going to take the given information about my limiting reactant. So I'm going to start with 0.500. My pen keeps cutting out on me, sorry. Moles of H2O2. I would bring moles of H2O2 to the bottom, And then I convert that into moles of my excess reactant, so moles of N2H4. So I'm starting with one reactant now, and I'm turning that into my other reactant to figure out, okay, if I used up all of my limiting reactant to make the maximum amount of product that that reactant could possibly make, how much of this was required to react with it? So then, yeah.
Is this one of the steps towards?
Say that again?
Is this one of the steps for remote?
Yes, that's why I'm using red. Yes, this is to use your given information to calculate everything else. So it's kind of vague because everything else just means any other questions that I ask you. So moles of N2H4, I have 1 mole of N2H4 for every 2 moles of H2O2. So 0.5 divided by 2 means that I would have used 0.25 moles of N2H4. So that is how much used to react with 0.500 moles. I keep forgetting to put the extra 0 on the end for sig figs. Make sure that you're paying attention to that kind of thing. So 0.250 moles of N2H4 used to react with 0.500 moles of H2O2. If that is how much was used to react with it, then to figure out what was not used in the reaction, I would need to take how much of my excess reactant I started with, which was 0.75 moles. So I would take, I'm just going to use like a different color for all of this. So 0.75 moles of N2H4. That's how much N2H4 I started with. Then I just showed that I used this much. So subtract 0.25 moles of N2H4, which leaves me with an excess of how much? Good. 0.5, and then in this case, I think that the 7.5, yeah, so that only has 2 sig figs, so your final answer should have only 2 sig figs. So 0.5 moles, what? Oh, thank you, thank you. 0.50 moles of N2H4. That is what was unchanged, so this would be the amount that is unreacted throughout the course of the reaction. And then letter C, we'll stop after this one. It says how much of each product in moles is formed. So again, this takes a little bit of critical thinking about what your numbers actually mean. If I have this much, there's like so many scribbles happening. I'm erasing just so we can see it better. If I started with this much N2H4 and this much H2O2, what is the maximum amount of N2 that I could make from this? We've already calculated it. 0.25, because the least amount made is going to be the maximum. It's going to cut out after that, right? So that's why we use the limiting reactants number to calculate everything else. So we have already figured out for the reactant, or for the product, N2, we could only make 0.250 moles. And I don't have to recalculate that because I already did my calculations. I already showed my work. It's all part of the same question. But I did not calculate how much of my other product, H2O, I could make. So now I'm going to still use my limiting reactants number. So I'll go back to red for this. And I'm going to say 0.500 moles of H2O2. And I'm going to bring moles of H2O2 to the bottom and put moles of my other product, my H2O, at the top. And then I turn my 2 moles of H2O2 into 4 moles. Okay, so 4 and 2. 0.5 times 4 would give me 2. Divided by 2 tells me how many moles of H2O could be produced. Okay, so then I would say for H2O equals 1.1 0.00, so it has the same number of sig figs, moles produced from these two things.